Okay, so I will present the paper Real-Time Edge Neuromorphic Testing from Chemical Microsensor Arrays that has been published in collaboration with members of the Institute of Neuroinformatics in Zurich. So the work focuses on the online monitoring of drinkable liquids and key sectors like water management and beverage manufacturing must respond fast and reliably in front of the contamination and the adulteration of products. They also have to comply with increasingly strict global regulations. In practice, this means rising demand for affordable instrumentation that should be capable to monitor multiple variables in situ and to do it in real time. But the reality is that most of these measurements are still performed in the labs or in using sizable and power-hungry instrumentation that is limited to a few parameters. In both cases, costs are high and the measurements are restricted to just a few locations. Measuring in the labs can also introduce considerable delays. To meet this challenge, we follow a Bioinspired approach. In our tongues, we have these cells that are sensitive to different molecules and that transmit electrical signals to our brains. Brains are then responsible for post-processing the sensory data to perceive the different tastes and to discriminate between different kinds of foods and beverages. Similar to the way we work, we employ an array of selective but non-specific chemical microsensors, and these microsensors can be read out and their responses can also be translated into sparse neuron-like electrical signals for posterior post-processing via a neuromorphic processor like the Intel Loihi in order to perform efficient qualitative or quantitative analysis on the edge. For this concrete study, we decided to discriminate between 5 different beverages. So we have cava, we have white wine, red wine, sparkling water, and still water. For this task, we used 9 different sensors, one PT100 for temperature, 2 platinum electrodes for oxide reduction potential and conductivity, and 6 different ISFETs to, that are selective to different concentrations of the ions. These sensors were read out via USB to a laptop, and the data was post-processed on the edge using a USB neuromorphic stick. To train the neural networks, algorithms that we employ to classify the different beverages, we created a dataset, MicroBe, that is openly accessible in Zenodo. So the dataset includes dynamic data collected from the 9 sensors that I said before, including sensor drifts and replacements. And we collected 5 minutes of data per label using different permutations of the beverages. So in total, we have more than 26,000 samples, and I think it was 1,500 of them were used for test. To classify the beverages, we used a causal convolutional neural network with one input channel per each sensor and 3 convolutional hidden layers with 32 kernels and size 4. In the end, we saw that using 7 of the 9 sensors provided the best accuracy. The INN was converted to a spiking neural network. By ANN, I mean the artificial neural network, the standard one. And it was converted to this domain, to the spiking domain, using the SNN toolbox created by Bodo Rueckauer. To this end, we created, we connected the inputs as bias currents to the input layer, performed weight normalization, and used spiking softmax. Results from neuromorphic classification, show high accuracy with less than 3% drop with respect to a standard artificial neural networks. And in contrast, the energy autonomy was considerably boosted to, as you can see, like 50 times lower power consumption and 15 times more energy efficiency that commercial edge artificial intelligence devices like the Intel Movidius USB stick. All these results were achieved running the neural networks, the inference of the neural networks, 180 times faster than the sampling period used for the sensors, that is 1 second. So in a nutshell, we presented the first neuromorphic portable implementation of electrochemical analysis. And the system is capable to continuously taste different beverages from chemical microsensors that have been manufactured at the GTQ group in Barcelona, and classifies them in real time with high accuracy and 15 times higher energy efficiency than commercial devices available today in the market for edge computing. So that's all. Thank you very much for your attention, and I'm ready for questions.
Thank you, Chema, for the presentation. It was on time, so that's perfect. We have César now. I don't know if César has time to stay like the 15 minutes you have left,
yeah,
or if you have to do it quickly.
No, I've got 10 to 15 minutes to show you.
Okay. Then I will launch the question of Margarit now, and then I will give you the microphone. César. Okay. The question for today, for this first presentation, that you can answer now in your computers, and we will talk about it later, is what do we understand by a neuromorphic device? A device whose shape resembles a neuron. B, a device that implements an artificial neural network. Or C, a device that emulates key sensory and or computational principles of the nervous systems. The first answers are coming in. There is a bit of debate, but it looks like everybody's sure of the answer. Okay, we will leave it open just for 1 minute and then we will close it. 16 out of 28, 57% have participated. Now we are reaching 70. Okay, we'll wait a couple of minutes. César, if you want to start sharing your screen.
Okay.
And then we will start with the Q&A of everything we've seen. Okay,
do you see my screen?
Yes, it's not on Okay, now it's full
Right.
mode. Okay, I will close the quiz now, and we will come back to it later. And César, whenever you want.
Okay, so good morning, good afternoon, everyone. So I'm gonna just give you some details about the last paper that we've published, which is entitled An Array of Individually Addressable two-electrode electrochemical cells sharing a single counter-reference electrode for multiplexed enzyme activity measurements. It's a bit too long title. So it has been published in Biosensors and Bioelectronics. And what you're seeing on this slide is just the slide that we sent to the TV just at the entrance at the reception, so that perhaps you'd seen this. So we worked on this on the development of this electrochemical array of electrochemical cells that have got like a particular two-electrode architecture that I will explain to you. Just looking trying to get like a compact configuration, and that could be useful for multiplexed analysis of different biomarkers in biological fluids. So we, as a first approach, we applied this transducer array to the simultaneous chronobarometric measurement of different enzyme activities. And we will show you the potential to be applied in electrochemical immunosensors in flow conditions. So the array consists of 5 two-electrode electrochemical cells that share a counter-reference electrode. And one of the particular features of this transducer array is that one of these, the counter-reference electrode, shares like just one contact path. But still, this could be compartmentalized to get like the 5 electrochemical cells in the array. So there you could see, the different components of this array, where you've got the 5 working electrodes of each electrochemical cell, the counter-reference electrode that has been divided into these 5 areas, like by using a silicon oxide passivation layer, and also the 6 contact paths, 5 for the working electrodes and 1 for the shared counter-reference electrode. So the fabrication process made use of standard techniques, like we deposit like a thin film of gold by evaporation, 100 nanometer thick film gold layer that was patterned by standard photolithography and wet etching process. And then we deposit a silicon oxide layer on top to passivate those areas that we wanted to isolate from the solution. That is all the electrical tracks and these areas just to define the counter-reference electrodes of the different electrochemical cells. So we package this transducer array using a PMMA cartridge that was fabricated by rapid prototyping techniques. And there you could see a design of this cartridge and a picture of the actual cartridge that was used for all the analytical measurements that were carried out. So I told you that we've got a two-electrode electrochemical cells in the array. But the standard electrochemical cells that are normally used in electrochemistry are 3-electrode electrochemical cells, where you could just detect electrochemical process taking place at the working electrode solution interface, while neglecting all the electrochemical processes that may take place in the counter electrode that we've got in the same electrochemical cell. So we've got the 3 electrodes, the working, the counter, and the reference electrode. So the potential in the working electrode is measured against this reference electrode potential, and what the potentiostat, when you work in potentiostatic mode with this electrochemical cell, the current is injected at the counter electrode to keep the potential between the working and the reference electrode constant, while the electrochemical process that we want to carry out in the working electrode is taking place. What happens when we go to a two-electrode configuration where the counter and reference electrode is the same one? So what we are measuring is just the potential difference between the counter reference electrode and the working electrode. And in this case, well, it is difficult to keep the potential of this reference electrode because this is being just polarized. Because it works as a counter electrode as well. So in order to use this kind of two-electrode electrochemical electrode arrangements for amperometric measurements, what has been published before is the use of silver chloride reference electrodes as counter electrodes as well in a solution that contains chloride ions, so that when the potential difference between the counter reference electrode and the working electrode is set, silver chloride is generated, and the generation of silver chloride produces the current that is required for closing the circuit in your electrochemical cell. But when you work with two electrodes that are made of the same material, in this case a metal, in order to inject a current in this counter reference electrode, you need like another electrochemical molecule that does so. So what we established was the use of redox pairs of molecules that are reversibly oxidized and reduced, so that when we measure one of these molecules at the working electrode by an oxidation or a reduction process, the counterpart of this molecule is being oxidized to reduced at the counter electrode, and then the current is generated inside the system. So we carry out all the analytical experiments required for optimizing this process and for assessing the performance of our two-electrode electrochemical cells. And we compare this with a three-electrode electrochemical cell configuration using a silver chloride reference electrode. And on the left-hand side, you could see that well, there was a shift in the potential when we moved from the three-electrode cell to the two-electrode cell, but the signals, the electrochemical signals that were recorded were pretty similar. And this was when we carried out potential scans, doing circuit voltammetric measurements, when we fixed the potential at which one of these molecules could be detected, in this case the ferricyanide, and we carried out the same experiment with the 3 and 2 electrode electrochemical arrangements. You could see that the responses to different concentrations of the redox pair that we wanted to measure were pretty similar. So this somewhat validated the performance of our 2 electrode electrochemical cells for carrying out chronoamperometric measurements. So we carried out some analytical measurements with this redox species with ferricyanide, and we quantified this molecule using our transducer array. And here you could see the circuit voltammograms that was used, and when all the cells were used in the transducer array, and also the chronoamperometric measurements that were recorded for different concentrations of this ferricyanide redox molecule. On the right-hand side, you could see the calibration curve that was showing us that this target molecule could be quantitatively detected using our transducer array. So using the same molecule, this molecule could be used as a redox mediator of the activity of one enzyme, which is a peroxidase. And so that using the same detection approach, we could detect, or we could measure the activity of this enzyme. And that's what I'm showing you on this slide. One is the enzyme reaction using this ferricyanide as mediator of the reaction, and also the electrodic process. you could see the circuit voltammetric measurement.
César?
See?
No, the last 30 seconds were frozen.
Okay, are you hearing me?
Yes, now.
Okay. No, I was trying to show you the measurements that we carried out for detecting the peroxidase activity using the ferricyanide as redox mediator. And there you could see the chronamperometric responses that were recorded for different concentrations of the enzyme and the calibration curve that was extracted for these measurements. But we could only, we were working not only with this redox mediator, with this redox molecule, but with other redox molecules that could also be reversibly oxidized or reduced on using our electrochemical cells. And in this case, we work with this hydroquinone. Hydroquinone is produced also by the activity of other enzyme, which is phosphatase, alkaline phosphatase. And then the hydroquinone generated in this enzymatic reaction could be detected using our transducer array. So you could see the circuit voltammetric response to the presence of hydroquinone and the oxidized molecule of hydroquinone, which is benzoquinone, the chronamperometric response of our transducer array to different concentrations of this enzyme, of the alkaline phosphatase, and also the calibration curve that was extracted from these chronamperometric measurements. And the last slide, well, I'm just giving you some hints about the potential application of this transducer array in the development of an electrochemical point-of-care device that has been already developed for the detection of different biomarkers in sputum, biomarkers that are related to the chronic obstructive pulmonary disease. And so we were detecting, we were measuring, three different biomarkers. And one was this cytokine, TNF-alpha. So in this case, on this slide, what you could see is the coupling of our transducer array with a paper fluidic component inside this cartridge, and how this device works. Well, we carried out a sample pretreatment using magnetic nanoparticles modified with an antibody that selectively detects this TNF-alpha in this case, and then we use another antibody that is labeled with HRP and carried out the detection using a reversible redox pair that is produced during the enzymatic reaction of this label. And on the right, well, in the middle, you could see a picture of the actual device, and on the right-hand side, the measurements that we carried out with sputum samples of healthy individuals and also patients suffering from COPD. What you could see the difference in the response to this biomarker in the different samples, which somewhat like shows the potential application of our device for rapidly detecting this kind of target analytes. And this is it. I want to finish just by showing you some pictures of the co-authors of the paper, Manu, Tony, and Ángel, and to all of you, thank you for your attention.
Thank you, César. We will start the Q&A now, and first we will launch this last question about your presentation. I don't know if you can see it. Okay, now you should. The question is, what are the advantages of using a two-electrode electrochemical cell array in an array format? The array analytical performance is better than with the three-electrode configuration, A. B, one of the electrodes of the two-electrode configuration can be shared among all cells in the array. Or C, they can be more easily fabricated. Okay, first answers are coming in. Let me remind you that the answers are anonymous. We won't know anything about who answered each, so it doesn't really matter. This is just to get a sense of it. Okay, half of the people have answered. We will close in 10 seconds. 64%. Okay, it's been open 1 minute. I will close it now. And we will see the results of the first question about the first paper of Gemma Margarit, which was mainly the C. Was it correct?
Yep, it was.
Can you elaborate a little bit more?
Yeah, sure. So a neuromorphic device is not just a device that implements a neural network, but it's a device that, beyond implementing a neural network, also does it in a way that follows the principles of our own nervous system. That means using the kind of signaling that our neurons use, which is efficient signaling in the terms that, it's sparse and it's not continuously sent, but sent when there are changes that represent meaningful information. And also in the sense that the computation is performed in parallel, sharing the memory and what we could say the computational units in the same cell, as our neurons do as well.
Okay, perfect. And now with the second one, or the second paper, César, the unanimous answer was also the B. Was it correct?
It is.
Can you elaborate a little bit more?
Yeah, that's the particular feature of our transducer array, that it shares this counter-reference electrode among all the cells. That if you've got an electrochemical transducer array, even if they are a two-electrode electrochemical cells, you will have a number of contact paths that will be doubled in the number of cells. And in this case, what we've got is 5 cells and just 6 contact paths. That reduces the size of the transducer array like quite a lot. And what we saw is that even if we've got this contact path and we are just compartmentalizing the counter-reference electrode among the different cells, that the performance of those cells has not been like limited at all. I mean that the performance is very good, and it compares with the performance of a conventional 3-electrode electrochemical cell that are normally used in electroanalytical measurements.
Okay, perfect. And now we have 5 minutes for the people to ask their questions, if there are any. Go ahead and turn on your microphones if you want. We have both researchers here willing to answer, we hope. Okay. Doesn't look like anybody is going to ask any question. Okay, Luis, go ahead.
I have a question for Chema. You said regarding the energy efficiency of your approach that it was better than a commercial device. And I think I recall 2 figures, that the energy efficiency was better by 15%, but the power consumption was going down by 50%. So which is the difference? How do you understand the energy efficiency in this sort of approach or devices?
Yeah, sure. So I will try to recover the slide first. Let's see if I can share the screen. This is here. So I guess you are referring to this slide, right?
Yeah.
Yeah. Okay, so power consumption is in terms of watts, and the energy consumption takes also into account the time that is devoted to inference. So that would be power consumption times the inference time.
Okay.
So in the case, why is the energy efficiency a bit lower than the gains that we get in the power consumption, in terms of power consumption. This is due to the fact that if you check this second table here, the inference time that we need for the neuromorphic device is 2 or 3 times higher. Can you see this? It's like 6 milliseconds. While using a Movidius device, it's 2 milliseconds.
And this is something inherent to your approach, or can we improve this 6 milliseconds of inference?
This depends on the accuracy that you want, because you need, as I said before, the data is transmitted as spikes in the spiking domain, and you need to accumulate these spikes in order to perform to average them, to count them, and average the noise. So in the end, So depending, the longer or the larger the time that you devote to that, the best the accuracy is as well.
Thank you.
So in this case, we adjusted the time to be 6 milliseconds because it's still 180 times lower than the time that we use for sampling from the sensors. And we could achieve already 97% accuracy with these 6 milliseconds.
Thank you.
You're welcome.
Thank you, Luis. Okay, any other question? You can also put them on the chat and we will read them anyway. Okay, it doesn't look like it. Any comment you want to add, either Cesar or Chema?
I say just thank you for attending the presentations.
Okay.
Yeah, thanks to all of you for listening to us. That's all.
Yeah, this is it for today. The presentation will be available on YouTube, and thank you very much, both of you, for the presentation and your time, and everyone who attended today. We will see each other next week with another Friday talk. So thank you very much. Have a good weekend. Bye.
Thank you. You too. Bye-bye.
Bye-bye.
Bye-bye, everyone.